So what we're going to take a look at here is a new concept. We're going to look at limits, something that we're going to study really for the next few weeks moving forward. And it's going to be the first calculus concept, but we're going to look kind of at a basic level today. All we're going to look at here is we're going to look at the sequence 1/2 to the x. And what I want to identify is the first 10 terms of that sequence. So how I find those 10 terms, I'm just going to plug in the values 1, 2, 3, 4, 5, and I'm going to end up graphing them. So if I plug in 1, I would have 1/2 to the first, so I would have the point 1, 1/2. If I plugged in 2, I would have 1/2 squared, and I would have 1/4, because that would end up being 1/2 squared. Now, what I'm going to end up going through and doing is really, you would have to go through, 1/2 to the third, you would have to go through and plug in all of these values, and you'd keep getting, oh wow, that's my fault, that's a mistake there. All right, that should be, when I plug in 2, I get 1/4, if I plug in 3, I get 1/8. My bad there. But, and really you're going to kind of keep going through this pattern. When I plug in 4, I would get 1/16. When I plug in 5, I'm going to get 1/32. And you guys can really go through and do the rest of it. Now, when I actually look at this and graph it, I apologize now just because looking at the smartboard, there's no lines. So I'm sure it's going to be totally off for the video because on the computer screen there's lines, but here there's not. So when I look at this, we'll say right here is 1. We'll go 1, 2, 3, 4, 5, 6, 7, and we good on the rest of it. All right, so I would plot these points. So I would have 1, 1/2 around here. I would have 2, 1/4, 3, 1/8, 4, 1/16, 5, 1/32, 6, 1/64, 1/28, and it's going to continue to kind of bottom out here. And really the important thing to look here is you want to be able to look at these graphs and see, well, as my x values get very, very, very large, so you want to kind of think back to end behavior back in Algebra 2. As my x values get really, really large, what is the graph actually approaching? And if you look at this, I'm sure you can continue the trend. You know, it's just kind of leveling out, getting closer and closer to 0. It's not approaching infinity or negative infinity like it would back in Algebra 2, but it's getting closer and closer to 0. And that's really the idea of a limit. Limits are basically going to be end behavior, and except it's not always going to just approach infinity or negative infinity. It may approach numbers. And if I look at this, it's slowly but steadily approaching 0. And that's kind of the purpose of looking here. Okay? So now, this is the actual graph. All right, so I have 1/2 to the n, or 1/2 to the x. If we're talking about this in limit notation, you're always going to have something written in this format. What it is by this part here, I have lim as n approaches infinity. That's how that's read. So what I'm looking for is the limit as my n values in some sequence get closer and closer to infinity. So if I'm looking at a graph, that would be as I move farther and farther to the right. Now, this is an actual graph of 1/2 to the x. So we found a few points on it before. You know, we found the point 1.5. You know, 1, 1/2 on the last slide. We found 2, 1/4. All those same points. This is just the actual curve for it. Now, what we want to think of a limit as it says right there in the red, we want to look, what is our graph approaching as n gets larger and larger? And it really is end behavior. And if you look at this, you can see as my n values go really far right, even already at 6 and 8, it looks like it's already basically 0. And that pattern will continue as we move farther and farther to the right. So what that's telling me is the limit down here, the limit as n approaches infinity of our function. That's always how it's going to be written. It's going to say limit as n approaches some value. So in this case, it's infinity. So as we go really far to the right for a given function, what y value are we getting closer and closer to? It would be 0 here. You know, we start to get closer and closer to 0, and it's never going to actually get to 0, just like asymptotes when you were looking back at exponential functions in Algebra 2. The same idea, you're just going to kind of level out at that value. Same idea here. If I take a look, I would have the limit as n approaches infinity of 3/4 to the n minus 2. Looking at the graph, it's nice. It's just like end behavior. I can look and see, well, what value am I actually getting closer and closer to? I know it's kind of hard to see on a smartboard, but you guys probably see it. As I go farther and farther to the right here, because what I'm looking for is as n goes to positive infinity. So as my n values, or really on a graph x, get larger and larger and larger, what y value am I getting closer and closer to? And if I take a look at this here, I can see, well, it's going to be equal to -2. Take that chair out of the way. All right, but that's really what I'm looking at when I look at limits graphically. I want to see what y value am I getting closer and closer to. It's basically the same thing as n behavior. And we should be able to see that here. And we're just looking as our n values go to infinity. So as we go farther and farther to the right. We can also look at the same exact thing as our limit as n goes to negative infinity of the same exact function. So if I look at all of this, what I would say is, well, when n's going to negative infinity, that would be seeing things going this direction. You know, n values going farther and farther to the left, where's our graph going? I'm going to look and see, well, here's my function. The graph of my function is shown. What y value am I getting closer and closer to? Positive infinity. As I go farther and farther to the left, the y value I'm getting closer and closer to, we can see, if you follow the black part here, as I go farther and farther to the left, I'm going to keep going up forever. All right, that's something that we'll address more later on. For now, we're only going to look at things like this, when n is approaching positive infinity. That's all we'll look at. All right, now, when I look at something like this, there's a few different scenarios. I want to find the first 6 terms of this sequence. What I want you guys to go through and do is actually see if you can go through and do that. So what I'm going to do is I'm going to end up pausing the video. I'm going to give you a little, what I'd say actually, pause the video, go through, find the first 6 terms of this. How you do that? Plug in n equals 1 for the first one. So 1 plus -1 to the first divided by 1. So I'll be adding 1 plus -1, all right, which ends up being 0. And then I'm going to plot that point. 1, 0, we'll say about there. Again, I know my lines are probably all off. But I want you guys to keep doing that. Go through for 2, 3, 4, 5, and 6. All right, so pause the video now and do that. All right, so if we take a look at what we got here, and we see kind of how we end up going through and plotting these, what we notice, we should have these 6 points. All right, we should have 1, 0, 2, 3/2, 3, 2/3, 4, 5/4, 5, 4/5, and then 6, 7/6. Now, when I actually plotted these, I should notice a pattern. I should notice the points are starting to kind of home in on one value, because that's really the idea I want to think about. You know, when I look at what is my graph homing in on? What is it approaching? And if I look at this, it seems to be approaching the value 1. Now, you can look, these points are getting closer and closer to that value of 1. And I can tell you, the farther right you go, if you pick an n value of 10 or if you pick an n value of 100, the closer and closer you get to infinity, the closer and closer that number is going to actually get to being 1. So what I can tell you is, from all of this, what we should be able to take away is the limit as our n value gets larger. As we go farther and farther to the right in this sequence, our value is going to get, our y values, if we plotted it, we get closer and closer to 1. That's what we want to really take away from this. Okay, now, what we could do if we do not have a graph, there's going to be 2 different ways we could find these limits. One, and it really all depends on what we have. Do we have one n value or do we have more than one n value? For the ones that you're going to see in this video, there's only going to be one n value. How I would go through and solve this is I want to basically just go through and plug in really, really large numbers. So if I'm looking at the limit as n approaches infinity of the function sine 1/n, let me go back and just plug in, all right, well, I'm going to plug in a really large number for n. So say I plug in, 1/1,000,000, something like that. All right, that's practically going to be 0. The larger that number gets, the closer and closer I'm going to get to 0. So all I'm going to say is instead of looking at something crazy like that, I'm just going to change that to basic to 0. Because that 1/n, as I get larger and larger than n value, it's going to get closer and closer to 0. So then all I'm really looking at is sine of 0. Sine of 0 is 0. So what that's telling me is if I graph this, I had sine of 1/x. If I graph that, I would get closer and closer. My graph would home in on the value 0. If you don't trust it, plug it into Desmos. All you have to plug in is this part. And you should see as you go farther and farther to the right, you should see it's getting closer and closer to 0. Same idea on the other side. Plug in really, really large numbers. So if I'm going to go through and plug in 0.99, you know, 0.99 to the 10th. I'm going to plug in 0.99 to the 100, 0.99 to the 1,000, 0.99 to the 10,000. I need your calculator to do that. So after I use my calculator, plug in all those values, this is what I'm seeing. So as my n values get large, I go 10, 100, 1,000, 2,000. My number's getting closer and closer to 0. So if I graph this, you know, 0.99 to the n, I would see on the graph that it's getting closer and closer to 0. And again, you could plug that into Desmos if you'd like. Just do 0.99 raised to the x, and you should see as you go farther and farther right, it should home in on the value 0. Just like when we talk about back here, this is, as we go to the right, it's homing in, and we go to the right, it's homing in on the value of -2. As I looked at that first one here, that homed in on the value of 0. That gets closer and closer to 0. So that's why our limit is equal to 0. That's why our limit, as our n values go really far to the right, is equal to -2. That's the y value it's approaching when we look at this. Now, this is going to be an important theorem for you to write down. Make sure you put this somewhere. And what we should notice is if the value here, you know, if we have an r value that's an absolute value that is less than 1, then the limit as n approaches infinity for r to the n is going to be equal to 0. Just like when we had 0.99 raised to the n, when we had 1/2 raised to the n, even if we had a -1/2 raised to the n, anything like this, as our values get really, really large, if I'm looking at the limit as n approaches infinity for any of these things, limit as n approaches infinity. If I'm looking at any of those limits as our n values get really large, they're all going to approach 0. All of the graphs would home in on 0. You can either plug in large values to check that, you can think about it in terms of a graph, or you can just use this theorem, understanding that if that rate is less than 1 that I'm continuously multiplying by, it's going to home in on 0. Now, one other kind of thing here. First 6 terms of this sequence, just like before, I want you to go through, plug in 1 through 6. So I would plug in -1 raised to the 1 plus 1 times 1 over 1 plus 1. All right, so I would go through and say, well, that's -1 squared times 1 over 2. That ends up coming out to be 1/2. So I would have the points 1, 1/2. I want you to go through and do the same thing for 2, 3, 4, 5, and 6. Pause the video. I'll go through and I'll kind of do the rest of this, but just do that for me. You guys actually pause and plug some of these numbers in because it was good to kind of do a little computation there. But if I look and I graph these things, these would be the points that I would have. And when I look at this graph is a little bit different than the last ones because it doesn't really home in on one value. If I look at it, some of the values are kind of look like they're approaching 1, some are approaching -1, and that behavior would continue forever. It's always going to kind of bounce back and forth if I were to look at this. That's an issue. We can't really work with that. So what we end up saying here is if I were looking at the limit of this, if I was looking to see what value is that homing in on, that's not homing in on some value. So what I would say is there is no limit, or it does not exist. Instead of writing that out every time, we're just going to write DNE. It does not exist. There's no limit. There's no one value that we're homing in on that is actually approaching when I look at this. Okay? So basically what we could say is there's a few different kinds of limits we can have. They can be convergent, divergent, or have no limit, having ones not exist. If we have a sequence that has a limit and it approaches some finite number, it's going to be convergent. So if it approaches 0, which we've seen a lot of, that means we have a limit. If it approaches something like one of this, if it approaches 1, like our graph here did, that would be convergent. It converges to 1. If I was looking at this, our graph converges to -2, as long as we're going farther and farther to the right. Okay, that would be convergent. What we can also say is if we have no limit, it doesn't home in on one value, just like we saw on this last slide. That would be does not exist. It does not go to one value. And when we look at divergent, it's going to be it approaches either infinity or negative infinity. So if I look at this one I have here, the limit as n approaches infinity of 4n minus 1. If I was plugging in values, that's a linear function. That's going to have behavior that looks like this. I don't even have to really look at the exact graph to know that. All right, slope of 4, y-intercept of -1, and that behavior is going to continue forever. And if I look at this, here's my x and y grid. Ooh, no, that's way off. All right, and it looks up and y-intercept would be down there. All right, but if I'm going to look at this, now I'm going to see as my n values go farther and farther to the right, I'm going to see that my y value is homing in on infinity. It's getting closer and closer to infinity. So the limit as n approaches infinity for that graph or for that sequence or function is going to be infinity. And if I look at the one on the left, that's going to be, if you end up going through and plotting about a bunch of these points, you would find out that that one's going to not exist. -10 to the first is going to be -10, so it would be down here somewhere. -10 to the second is going to be 100. -10 to the third is going to be -1,000. And it would continue to just move farther and farther away in either direction. That doesn't home in on one value. That would be another case that does not exist. And really, I know I didn't go through too many points there, but it would end up looking just like this. Because I have something that's bouncing back and forth over the x-axis, it's not homing in on one single value. Even when I look at here, this divergent one, it's homing in on a single value. As I go to the right, it's getting closer and closer to infinity. It's getting larger and larger and larger. That's okay. It could also approach negative infinity. That's fine too. That's called a divergent sequence. So we can have convergent, divergent, or have no limit. All right, convergent is going towards a finite number. Divergent is going to one of the infinities, or there could be no limit. All right, so those are the important notes to kind of take away, and that's the foundation for everything that we're going to work moving forward. So again, even if you need to go through and watch this one more time, we have graphs, and really the important thing to take away is limits are what are we homing in on? What value are we getting closer to? If we don't have a graph and we have one n value, what we can do is plug in really large n values to figure it out. Basically that just showed us our behavior. If we take a look at this, we basically know what the graph's going to look like. It's going to get closer and closer to 0 just from these. And the same idea over here. It's going to get closer and closer to 0. And this key theorem is going to be important. Make sure you have that written down somewhere. When that r value there is less than 1, we're going to end up seeing that our limit's going to approach 0. That's all.